Okay, so let's go back to just a general function, f of x. Okay, so if this is our function f, and this is a, x represents just an input value, what are the coordinates at that point?
X, f of x.
Good. So we get the ordered pair x, f of x. And f of x could be anything, right? It could be, x is our input variable, f of x gives us our output values of the function. I mean, it could be a volume, it could be a profit function, it could be anything, right? If x changes by some amount, okay, so let's say that we're going to scoot to the right by an amount delta x. So then this point right here becomes x plus delta x. What are the coordinates at that point?
X plus delta x.
Okay, good. So that one is x plus delta x, f of x plus delta x, right? And if we want to find out, let's just say, for example, that that x represents maybe the radius of a ball bearing. We've gone into business to raise some money for a field trip here. We're making ball bearings, all ball bearings these days. And the ball bearings are very high quality ball bearings. We have to control the tolerances of the ball bearings very well, right? So we know what the radius is supposed to be. But inevitably, there's going to be a little bit of error, right? There's a little bit of error, and that error could be, would you agree that if this is the value of the radius that we're trying to hit, there's going to be a little bit of wiggle room there because we can only be so exacting, right? Who knows whether it's a millionth of an inch or, whatever it is, there's going to be a little plus or minus a fudge factor. That delta x could represent that, couldn't it? Right? So we're trying to shoot for a value of x, but we've got this delta x error, and it would go either way then, wouldn't it? We'd have delta x on this side, and we'd have x minus delta x would be the smallest possible actual value of our radius. X plus delta x would be the biggest possible value of our radius, even though we were shooting for x, right? What if we're calculating volume? If we're calculating the volume of our ball bearings, which would be, for example, that's going to be proportional to mass. And let's say we have to control the mass very carefully. So we're going to think about that in terms of maybe a volume, right? We can only afford so much of a change in the volume, or the mass would change by an unacceptable amount. Okay, that makes sense? All right, so then obviously this is not what a volume curve looks like, but just, for the sake of argument, pretend it is. Okay? Well then, would you agree that if I were to calculate the value of the function, which in this case stands for volume, at x plus delta x, that's going to give me the maximum volume that I could get as a result of my error in radius? Would you agree? And if I went x minus delta x, that would represent the minimum possible volume based on my error. Okay? That's what we call propagated error. So there's an error in radius that's going to be propagated into an possible error in the volume that we're calculating, right? Okay, so then how would we go about, if we know what our error in radius is, how would we go about calculating what the maximum possible volume would be based on our propagated error? Well, we could just find what the value of the function is at x plus delta x, right? Okay, that makes sense? We can do that. Our function is curvy here, it's not straight, right? But if the error is sufficiently small, like if this delta x is really small, what's that gonna, like, let's say the delta x was only just this wide instead. So we went from there to there. Well, now, if I focus in on just that little part of the curve, would you agree that it starts to look straighter? It starts to look pretty linear, doesn't it? Even though the curve, if we zoom out, we can see it's very curvy. If we zoom in to just this very small incremental change in x, to plus or minus delta x, it looks pretty linear, right? And so we can take a shortcut here. This is called a linear approximation or linearization. We can say, okay, as long as our error is relatively small, right, we could make this a much, much simpler thing to calculate by just, instead of looking at the value of the curvy function at x plus delta x or x minus delta x, let's just approximate the function with a line, right? And as long as we're close to x, the line is a very good approximation of the function, okay? So what can you tell me about this line? If it's a tangent line to the curve, what's the slope of that line going to equal? Say it's the point where it touches, right? Okay, it's the slope at that point. You're right. So if we're calculating the y values or the output values are given to us by f of x, what's the slope of that tangent line? Think calculus. It's the derivative, isn't it? Right? We know that dy dx is just f prime of x, isn't it? Right? Okay, well, think now in terms of what this, let's make a connection between the slope of this line and our traditional slope formula and the meaning of dy dx, right? Going clear back to algebra 1, haven't we said that slope just equals rise over run, change in y over change in x, right? So just to make things look a little bit bigger here so you can see the drawing better, let's go back to a slightly larger delta x, right? If I want to calculate how far the line has moved up or the function has moved up, I already defined this distance as delta x. Let's call this distance delta y. That's the actual change in the function, right? If we move to the right by an amount delta x, how much did the function increase? Well, really all we did is we went from a y value of f of x to a y value of f of x plus delta x, right? So then what's the definition of delta y? How much did the y value change? Well, if the ant walked from this point to this point, how much did it go up? Say it again. Okay, but don't make this, I mean, just think about the coordinates of this. What if this was the point 10, 10, and this is the point 11, 12? How much did it go up? 2. How'd you find out? What'd you do?
12 minus 10.
12 minus 10, right? Yeah. The
X.
final y value minus the initial y value told you how much the y value increased, right? Okay, well, let's not be specific. This is f of x, and this is f of x plus delta x. How much did the y value change?
F of x plus delta x minus f of x.
Make sense? That's the actual change in the function. But what if we called this distance right here? This is our line, right? What if we called this distance right here dy? Okay. And we could say that instead of calling this delta x, let's just call this distance right there, let's also call it, dx. Right? We've gone over along the line. We've moved over some distance dx, and the line has moved up some distance dy. Well, that makes sense, doesn't it? Now, that fits the pattern of our traditional slope formula, right? Slope is rise over run. Well, as the ant walks along the line instead of the curve to get from this point to this point, he ran by dx, and he rose by dy, right? That's all that's saying right there. That's just the definition of slope, right? Rise over run equals the derivative of the function at x, and that's what calculus told us that a derivative does. It tells us the slope of a tangent to a curve at any value of x, right? So we know from our extensive discussions of calculus that this means the slope of the tangent line, right? We know from algebra 1 that that means the slope of a tangent line, right? Go away. Right? Rise over run. Does that make sense? Okay. So then if I want to find out how much the line has increased, how much the y value has increased when the ant walks along the line from point A to point B, well, isn't that just dy instead of delta y? They're not exactly the same, but they're pretty close as long as dx is smaller, delta x. Right? As long as the incremental, if I've only moved to the right by a little bit, you guys agreed with me that if this distance from x is very small, the curve is not very curvy. It looks pretty linear, right? And so the line is a good approximation. If I get too far away, the line's a very poor approximation because the curve curves away from it, right? But if it's small, it's pretty good. So then we could say that dy, this amount right here, that the line has changed, which is going to approximate how much the curve has changed, is what? Well, if I solve for dy, what do I get?
Prime of x divided by dx.
Yeah, f prime of x times dx, right? This is what we call the differential form of a derivative. Okay, and why is it the differential form of a derivative? I don't know exactly why they gave it the name differential, but it just tells us for a given change in the x value, it tells us what the differential is in the y value. How much did the y value change by itself? Not with respect to the x value, but just by itself. How much did the incremental change in the function add up to, right? What is that dy? Okay? We can take any of our original derivatives that we've written in normal derivative form, in ratio form. Like, for example, we know that the derivative with respect to x of sine x equals what? Good. If I wanted to write that in differential form, what do you think I would do? Yeah. I would say the derivative of sine x equals cosine x times dx. And what does that mean? That means that on this particular function, if I nudge horizontally by dx, this predicts how much I'm going to move vertically based on that small nudge. I'm going to move up by cosine of whatever my x value is times whatever the magnitude of my small horizontal nudge is. Okay? So it means a different thing. It's different than saying, this is telling me, when I write it this way, my derivative means, what's the slope of a sine function at x? Well, it's cosine x, right? This is telling us that a small horizontal nudge of a sine function is going to nudge us vertically by that amount. Okay? I mean, they're strongly related, but they actually answer different questions. Okay, so now let's take what we just came up with here then. We said that delta y is equal to this. Dy is equal to f prime of x dx. And delta y and dy are approximately equal, right? So this could be pretty useful to us. Let's take a real life situation now. Instead of taking x and f of x, let's take our ball bearing situation. Let's take an actual volume function, right? And let's look at that, right? So what if we had, what is the formula for volume as a function of radius of a spherical ball bearing? 4/3 pi r cubed, okay? So what is the derivative of v with respect to r? Yeah, good, so dv dr is the same thing as v prime of r, and that is, what, say it again? 4 pi r squared, good. And so if I wanted to write this in differential form, that would look like dv equals what? dr, okay, good. So then if we've got this volume function, and we can graph a volume function if we want to, right? Volume function would just look like it's cubic, so it's just going to look like, that has no meaning on that side, does it, for volume? Because radius can't be negative, but if that's r and that's v, that's what the graph looks like. That's a cubic function, right? So what if we pick a certain value of the radius, and we've got some error in manufacturing our ball bearings of, we could call it delta r, but really it also means dr. And we want to estimate how much is the volume going to change based on our error in measuring or producing radius, right? Technically it's delta r, but that's, if I want to calculate delta r, or delta v, I've got to actually calculate the volume at both parts of this and make it and subtract, and that's inconvenient. Let's just use our linear approximation instead. And let's say, okay, if the radius is going to be, what, 10 centimeters? I don't know, we're really big, let's say, okay. So we got these 10 centimeter huge ball bearings, right? Plus or minus, what's our error in measuring radius for these things? What do you think? I don't know, like 0.01 centimeters, okay? Plus or minus 0.01 centimeters is our radius. Let's figure out what's going to be the propagated error in terms of the volume, right? So dV is delta V, our actual propagated error, is approximated by dV, which is just that, right? 4 pi r squared dr. Well, what goes in for r? 10. What goes in for dr? 0.01, yeah. Right? That's going to give us, just that easy, we're going to get a fairly accurate, approximated propagated error, right? So let's plug in those values. 4 times pi times 10 centimeters squared times plus or minus 0.01 centimeters gives us what? Okay. I'll take your word for it. I want to get that number on our calculator here. So 4 pi times 10 squared, just 100, right? What's that? I just didn't put a multiplication between the pi. 10 squared, 100 times 0.01 gives us a value of about 12.56. What are the units going to be? Square centimeters times centimeters gives us...
It's just 4 pi centimeters squared.
Cubed, right?
Yeah.
Going to give us an answer in terms of cubic centimeters. So delta V is approximately equal to plus or minus 12.57 cubic centimeters.
It is just 4 pi though. The 10 squared and 0.0 cancels out.
What, did I do something wrong?
No, I'm just saying you could write it as
Easy
4
to
pi.
simplify.
We chose
could just wrote
1/100 of
a-
a centimeter and 100 centimeters.
Oh,
Yes.
yeah,
you
you're right,
could
this
write
is,
it.
you're right, I got you, I see your point. But so this is telling us then that the volume that we're producing in these ball bearings could vary by as much as 12.57 cubic centimeters above or below our target value.
That's a lot.
That's
Okay.
a huge amount.
Well, I don't know, is that a lot or not?
Yes.
If I'm asking you another
How
question.
long-
Yes,
how big are
okay, I'll
they?
take that,
Ball
yes.
bearings, it's-
Okay, so if I'm measuring, let's say I'm building something, and I can measure the linear dimensions by plus or minus an inch. Is that good or bad?
Bad.
Well, how big is it?
Exactly, how big is it?
It's bad still.
That's pretty bad if it's a foot wide, plus or minus an inch
So it's
is,
just like a mile.
that's pretty bad, right? But what if we're building a road that's gonna span 1,000 miles? Well, I'll take it. An inch is, plus or minus an inch is gonna be fine, right? So you see my point? The magnitude of the propagated air really,
Yeah.
the magnitude of the propagated air, really, it's hard to tell as an absolute number if that's good or bad. Only way we can tell is if we compare it to the value of the actual volume. Yeah.
Would an inch on the Golden Gate Bridge be bad? And I know it's already adjusted for like temperature changes, so it like flexes inside. Would an extra inch in
You know, it would be probably not great, but it probably wouldn't cripple the job either. You know, I mean, you probably could be, they very well might have been off by more than an inch based, you know, when they built the thing compared to their original design. That probably would be tolerable on a bridge that's several miles long, right? But it wouldn't be if we were building something that was, you know, we needed a fair degree of accuracy and it was supposed to be this size and it ended up being that size. Well, that's not good, right? That's gonna change the volume of that box by a lot. Yes, ma'am?
Will we ever use like the negative of 15 on like the negative 0.01?
Well, yeah, we did in a sense because we multiplied by plus or minus 0.1. So we really have both signs in there, which we need because the volume could either go up or down by that amount, right? Is that exact? No, it's not. It's not exact. This is an approximation, right? But as long as the dx, or in this case the dr, is relatively small, it's a pretty good, quick approximation, right? Okay, so but let's take this one small step further then. Is this good or bad? Who knows? But if we calculate, instead of calculating delta V, if we calculate the relative error, which is delta V over V, that makes more sense, right? Delta V over V, well, that's going to equal, in this case, plus or minus 12.57 cubic centimeters over my volume. Well, what is the volume at 10 centimeters? We could calculate that, couldn't we? Right? V of 10 is just 4/3 times pi times 10 centimeters cubed, right? So if we go back to our calculator, so 1,000, 10 cubed. Oops, went too far. There we go. Well, our volume is,
It's still like,
just divide that by
oh,
10.
yeah,
Divide that by
10.
10.
Okay. Is 4188.8, right, 0.79. Okay, so, is that good or bad? Well, I don't know, that seems not too bad. So we get, I'll just do 4189 now. So what's that give us then? If I divide this guy divided by that guy, we get a value of about 0.003. Okay? That still doesn't mean a lot to me. How could I write that in a way that's maybe a little more meaningful? Percentage, okay? So that's about 3.3% plus or minus 0.3%.
That's pretty big.
Is how much that might be. I mean, that might be too much for us to tolerate, right? But if you were actually, here's the thing, I mean, if you knew what your mass tolerances needed to be, I ought to be able to work backwards and develop a relationship between my mass or my volume tolerances, same thing, and my radius tolerances, right? And we did something here. We did a little more work than we needed to also, right? You get the idea that that's much more meaningful to write it as a percent, right? Percent error. Okay, but if we had thought about this from the beginning, and really what we were interested in was relative error, did we really need to even calculate what our differential was? No, we didn't, right? Delta V over V is approximately equal to dV over V, right? And dV we calculated up here to be 4 pi r squared dr, right? What's d? 4/3 pi r cubed, right? Before I even plug in values for r and dr, what could I do to that expression? Yeah, I could cancel tons of stuff. Right, I could cancel r squared and r squared. I could cancel my pi's. I could cancel my 4's. And I'd end up with 1/3 on the bottom becomes 3 on the top. Right? That's better, isn't it? That gives us a much more concise formula that tells us what our relative error is going to be in terms of my measurement error, right, and my target value, right? So what did we say? We said we want these things to have a radius of 10 centimeters plus or minus 0.01 centimeters. 0.1 or 0.001? What was it?
0.1.
0.1. Okay, so then our relative error is about equal to 3 times plus or minus 0.01 centimeters divided by 10 centimeters. Oh yeah, and by the way, what happened to the units up here when we calculated relative error? They canceled there and there. They should, right? If we're going to write this as a percentage, it's unitless. Unitless numbers are almost always, like in engineering, more useful than numbers with units, right? Because they're giving us a comparison. And comparative values are important, right? So we end up with plus or minus, what's this going to be? 0.01 divided by 10 is 0.001, right? Times 3. There we go. Right? Much easier. Yes, sir.
Just from a cautious standpoint, when you're approximating dV equals delta V, is there any time where that could get you in trouble or be wrong?
When you're, yeah, there is. Right, there is. If you're deviating too far from your target value, right? Remember, linearization, and we've talked about this in different ways throughout the year. Remember, linearization, or this linear approximation, is only good when you stay close to home, right? The Earth looks pretty darn flat if you're on a boat in the middle of a calm ocean, right? But it doesn't look very flat if you're standing on the moon, and you can block it out with your thumb, right? So as long as you're very close, and the distances you're traveling are small relative to the radius of the Earth, well, you can treat it as being pretty darn flat, and it works fine. We probably treat the floor as being flat here, don't we? Right? It's fine. Right? But in reality, is it? Well, probably not. Probably not. Right? Make sense? If you're on an icy pond, that's pretty flat. I mean, if you're going to have a regulation hockey game on a on an icy pond, you really need to go out there and take off and bevel it down so you take off that little bit of crown that's going to be due to the curvature of the earth? I don't think so, right? You're probably okay, aren't you? So yes, the answer is, as long as you're close to home, so the curve is well approximated by a line, you're fine. Okay? So what if then, hey, why don't you guys try one of these? Just so you, I mean, I'm just going to throw one up here and just do one, just to see how it works. Okay, here you go. Try. Number 35. $36. We've already done most of this work. What if you want to say you've got a shell with an average radius of 100 centimeters and its thickness is 0.2 centimeters, and you want to calculate what the approximate volume of that shell is? How could you do that? What do you think? I mean, isn't that kind of what we just did? Right? See what I'm saying? So what would you're calculating a volume, right? So what's the form? You know what the formula for volume is, right? And you're trying to really, just by calculating dV in this case, aren't you just calculating what an incremental little extra bit of shell would be on top of the original volume? Does that make sense? If we tweak the radius from 100 centimeters by plus or minus 0.2 centimeters, the amount that's changing the volume is the same thing as the extra volume that creates this shell, right? If the shell is hollow, see what I'm saying? Right? You've got, pretend it's perfect. If this thing is a perfect sphere with a radius of 100 centimeters, then it's got a volume that's easy to calculate. Let's say I'm going to freeze a thin layer of ice on top of that, right? Or let's say, I don't know, it starts off being ice, and we're going to put a thin layer of paint on the ice, and then we're just going to drain the ice out, put one small hole in the bottom, and let the water melt and drip out the bottom. Right, so we've got this thin little shell of paint left over. Well, if the paint has a thickness of 0.2 centimeters, what's the volume going to be? Approximately. Not exactly, approximately. Isn't that the same thing as saying this is R, this is dr, and we want to calculate the differential dV? How much did the volume change approximately when the radius changed by 0.2 centimeters? You get that? Okay. That was pretty, this is honestly, in a way, this was a very sneaky way of getting you thinking about calculus, the calculus of your futures. Because a lot of what we do in the future is we're going to do things like this, where we're going to say, let's calculate the volume of some sphere by just adding up all the incremental changes in volume from, as the radius goes from 0 up to 100. We could add up the incremental additions in volume of all those little dVs as the radius goes from 0 up to 100, and we could actually use calculus without a formula to calculate what the volume of that sphere is. Okay? But that's, I don't want to jump ahead too far. Okay? Does this make sense? Okay? So how would you do this one then? This is the one we just did, right? What if you wanted to calculate the approximate volume of this, looks like a running baton and track, right? It's just a hollow tube. It's got a height of 40 centimeters and a radius of 5 centimeters, and the thickness of the tube is 0.2. Okay? See if you can come up with an approximate volume. Doesn't have a top or bottom, it's hollow, just a tube. Okay. So once again, just think about the dV, approximated, or the delta V approximated by dV as just being that extra layer of paint that's going to be painted on the outside of this cylindrical icicle. And then we're going to let the ice melt out of the middle. Right? If it bothers you that this isn't exact, that's what engineering is all about. It's never exact, right? I mean, you're right. The radius is going to go from 5 to 5.2, but we don't care about that, right? We're just going to approximate the radius as 5, and we're going to say, okay, the radius is 5 is pretty close. The change in radius is 0.2. What does that do to the volume? Right? Okay, try that. By the way, what is the volume of a right circular cylinder? Pi r squared h. Good. Okay. But the height is fixed here, isn't it? Right? So in our case, it's going to be pi r squared times what? Times 40. Okay? Okay. What'd you get?
251.33.
Yeah. Is that what you guys did? Did you get that? 251.33? Oh, so you actually did a percentage. Okay.
I got the percentage and then took the percentage of.
Okay. In this one, though, if we're actually trying to calculate the approximate volume of the shell, in this case, what we're actually looking for is dV, right? Our approximation is dV. How much did the volume change? Does that make sense? This time we're not asking, slightly different question. This time we're not asking, how much does the volume change? We're actually saying, okay, if we take this one little change in radius, how much additional volume does that give us? It's a different meaning. This time it's not an error, right? At this time, if we start off with our formula, you already told me that V equals pi r squared h, and the h is 40, so this gives us 40 pi r squared, right? What's dv? Yeah, that's just going to be dv dr times dr, isn't it? Right? So it's going to be the derivative times dr. If we just write this in differential form, right? dv equals dv dr times dr. So that's 80 pi r dr, right? R is 5. The change in the radius, that's going to, the thickness of the paint is 0.2, right? And so we get dv equals 80 pi times 5 centimeters. Thickness is not plus or minus this time, it's just 0.2. And that gives us about, what was it again, 351.33?
251.33.
So that's dv. dv exactly equals that, but delta v is approximated by that. Is that the exact volume? No, it's not. It's not. It's an approximation, but it's pretty darn close, right? How would we calculate the exact volume?
Taking the volume of the.
Yeah, we take the volume of the, right, good, the volume of the whole thing, paint plus ice, minus the volume of the ice. It'd be slightly different, but not very much. Okay? All right, we'll continue with that.
So this, it doesn't equal like a dr, dv, this is just the relative error.
So this, was that the percentage?
Yeah, that was the.
Okay, right, so that's the relative error. That's saying, what that's saying is, how much does the overall volume, by what percentage does the volume change when you add the paint? So in other words, pretend you've got this cylindrical 40 centimeter tall icicle, right? It's got a certain volume. If I paint on a 0.2 centimeter thick coating of paint, by what percentage, roughly, did the volume increase of the whole thing? Well, adding the paint increased the volume by about 8%.
So then, when I'm doing that, is there a way, instead of having to solve it like that, if you could just do the 8 times?
Well, no. Okay, so in this case, I see what you're getting at. If you're just trying to find dv, it's easier. That easiest thing is just to calculate the differential and plug it in, right? Because it's more hassle to find dv divided by v and then cancel all that stuff, right? You see what I'm saying?
Yeah.
Yeah. Okay. Evan. Okay, on Friday. Okay, that's fine. That's fine. We'll do. I'll make a video. Yeah, I updated everything yesterday. I mean, it's not a big deal. I wouldn't be surprised. I mean, we're supposed to have. I'm surprised we didn't have snow day today, but I guess we've got like 2 weeks of this. So, yeah.
Really? I thought it was,
No. We're gonna have this for a little bit. So you never know. Maybe we can catch a break on Friday and get a snow day or something. I doubt it, but yeah, don't worry about it. You'll be fine. We're gonna
finish up the written tests.
Say that again.
I need to finish up my written tests.
That's fine. So you guys are gonna I have to be gone for 3 days, either 2 or 3 days. I'm not sure yet. Next week, and so you guys are gonna I'm gonna have a sub you guys will have nothing but time to work and test.
Okay.
And so I may build in 1 additional test day, but if not, you'll have days to do it then. So I'll probably save as much as I can for when I'm gone.
Okay.
Don't sweat it. You'll be fine.
Tomorrow, can I come by right after 4 and just finish up the last
Yeah,
paper?
that's fine. I can get you for TA any day too.
I don't have to.
Oh, I got you. Okay. Yeah, that's fine. Right after 4th works. Yep.
All right.
Mhm. Yep.